Hello, hello, testing, working.
Hey, can you hear me? Can see me?
Hey Ben, how's it going? Can you hear me? I can hear you. Looks like Ian's joining.
I hear you.
Yep.
My audio. You're muted.
I think we'll give everybody a few minutes to join.
Ian, can you say something so that I can hear you?
Yeah, I'm
No,
talking.
I'm not going to say anything.
Uh,
River. Check 1 2, check 3 4, check 5 6.
yeah,
Ben, can you hear?
maybe it's.
Ben is muted.
Yeah, I don't know if you can hear us. We can hear you, Ben.
Well, now I can't because he's muted.
Yeah.
Can you hear me now? No?
Yep.
Oh, I hear you. I hear you. Cool.
There's a little bit of
There's some sort of echo going on in there.
echo. Yeah.
Let's see my game.
Which is confusing because there's only one of you in the call.
Is that better or worse?
That is
Yeah, it's
better.
better.
That fixes it.
All right, cool. All right, if I stand far away, how's that?
There's a little stutter up in the audio, but
Check. Test.
Yeah, there's something janky going on.
Let me try. Hold on. Say something. They're not playing audio somewhere else.
Check 1 2, check 1 2. Yeah, it doesn't sound like you're.
let me mute
Definitely
myself, I guess.
All right, how's that? Echo? Check.
Keep on talking.
Check.
Yeah, there's still some sort of delayed echo thingy.
Do you have the YouTube up or something?
No, and I got audio going into my headphones anyway, so it shouldn't pick it up. Pretty impressive that it can still pick it up. How's that? Is that not
It's still
weird?
Yep. And it seems to be at the same volume too. So it's not like it's picking up from the headphones. It's just like it's recording things twice with a delay.
Try changing my mics maybe. Check. Any better now? Something?
Maybe.
Yeah. Hard to tell.
Try reading something like. I don't know.
I don't know. Austin PHP, May 2020. Staff engineer at Wayfair, PHP Town Hall.
Yeah, it's still.
Yeah, it's still.
All right, let me grab my Bluetooth and hopefully that won't be more.
Okay.
I guess maybe I should have not started the broadcast until we we're all ready, but yeah, that's okay.
What's fun with that? I mean, you gotta do it live, and so far it's just us anyway on this call. And my guess is, if I look back over at YouTube,
is there like a chat side on YouTube somewhere?
Yeah, there is if you enable it.
How do we enable that?
All
Chat
right,
is
how's that
disabled.
now? Any better? 1, 2, 3. Check 1, 2, 3.
I think that works.
It might be a little low. Try on the game. Try reading something.
Austin, PHP, May 2020. Ben Edmunds, staff engineer at Wayfair, phptownhall.com.
Yeah.
Okay. Yep.
Yeah.
We're good.
Cool.
Yeah.
That's with my AirPods, so hopefully they don't die or something. And if they do, we'll just have to scramble. I'll switch back if they do.
Yeah. Sounds good. Let me see if I can enable the chat on the YouTube. 1 second.
Yeah, the chat and Q&A on Zoom webinars in particular, and honestly even on standard Zoom, is just user unfriendly to a T.
How do y'all do this too? Will I see the attendees or will I just see y'all, or how's that work?
Since we're using webinar, you will not see attendees, nor will they be able to speak. They will be throwing stuff into Q&A or chat if we're talking about inside Zoom, and I can monitor the YouTube chat and see if anybody throws anything important there.
Cool.
Logan, have you found where to turn on chat within the YouTube stream? Because it seems to be disabled still.
Yeah, I'm looking for it. I'm like in the video edit page, and it's not there.
Okay, I'll see if I can hunt around from here.
Okay. You should have access to, or be able to switch to that account, right?
Yes, I believe so.
Okay. Cool. All right. Well, I guess we'll go ahead and get started, Ben, if you're ready. And Ian, if you're ready.
Let's wait till I would say let's wait a couple more minutes.
Okay.
Because we have 2 people extra attending on Zoom, and I'm not quite sure how many on YouTube. I'm checking that right now. Logan, did you get that link that I sent you in the organizers chat? That should show you how to turn live chat on.
Okay.
I hunted around on my account for the Awesome Tech Videos account to switch to, and I didn't see it, so I'll have to troubleshoot that later.
Yeah, I think we might have to figure it out after. It's I saw that and I don't see it. How to do it from the video page.
Okay. Can you double check and make sure that I do have delegated access to the ATX web video? Austin.
Account. Yeah.
Yeah, that account from mine.
Yep.
Thanks.
Yeah, I'll do that.
Cool. Suppose
All
we
right.
can...
Yeah, let's go ahead and get started.
Right.
Thank you all for joining us. Awesome PHP May 2020. Really excited for Ben's talk. He's an experienced speaker and spoke at all sorts of conferences before. Been a PHP developer for over a decade. I don't know if you've hit 2 decades yet, Ben, but you can tell us more about yourself. Certainly when we get into things here. A few announcements before we get started. I think we're switching over to this new format and open to feedback on the webinar stuff, and I think it'll go a lot smoother this month versus last month, and just interested to hear your all feedback. You're welcome to leave some Q&A if you want in the chat, the Zoom chat. If you go up to the Zoom bar and look for the Q&A button, you should be able to ask a question that way, and that way one of us, myself or Ian, will monitor that Q&A chat while Ben is speaking, and obviously you can ask questions in our Slack as well. And for those of you who might not know about our Slack channel, if you go to austinphpchat.com, there's a link there at the top. You can just click there and join. And so we'll be hanging out in Slack as well. So plenty of opportunities to engage with us. But our goal for this month is to make sure these virtual meetings go a lot smoother going forward. So but before we get into it, Ian, I wanted to see if you could give us an update on Longhorn PHP and what's going on with that.
Sure, thanks. So short version is it's still happening. We're still planning on hosting an in-person event in mid-October. The dates haven't changed since we announced the conference, and the venue is still at Holiday Inn Midtown, near 35 and 290. Now, if we're committed to running an in-person event, even if that means postponing, at least at this point. So tickets are available right now, and of course will remain valid. And on the other hand, if you want a refund, you can get one if we do decide to postpone, which we're watching closely how things are reopening and what's happening there. We'll make a decision on whether to carry on as is or postpone over the next few months. Currently, the CFP is open, and we've pushed the deadline a bit on the CFP. So now get your talks in by the end of June. And yeah, that's basically all I've got. The thing is still happening, still planning on doing it in person and letting everybody who's doing an online conference kind of have a monopoly on that format. and we'll see what happens.
Awesome. Looking forward to another great Longhorn PHP, and I'm hopeful that 2020 we can make it happen. So great. Well, Ben, if you're ready, I don't know if I have to stop sharing how that works, but you should have permissions and all that sort of stuff if you want to give it a go and swap over to your screen there.
Cool. Let's do it. Let's see if this plays.
Cool. It works.
All right. You see the presentation and the one without the speaker notes.
Yep.
All right. Cool. Hey, thanks for having me, everyone. I'm here to talk about web scale, system design, and architecture. Who am I? I'm Ben Edmunds. I do some open source work. I have a couple books on PHP and Node for securing applications. I do the PHP Town Hall podcast with my good buddy, Matt Trask. And I'm a staff engineer at Wayfair, and I work on the development platforms team. And our goal is to build development platforms for thousands of engineers. We actually have over 1,000 PHP engineers at Wayfair. Today, we're going to cover 3 main areas. So we're going to cover design principles, which is really the code level of your app. And then we're going to zoom out a little bit and cover the application architectures of your app. And then zoom out even more and cover the platform architectures. And that's going to cover both the platform and the data architectures. And then we'll end the presentation with a kind of quick system design to help you see how I would think about both the design of the system and the scaling of that system, and then how it changes over time. So we'll start off with design principles, and I'm going to tell you a little story. So this was my second job ever. I was very green, right? And so I was working at this manufacturing facility coding for these manufacturing robots. And so these robots would take various parts down a production line, and they would weld the parts together, and then at the end of the line, you would get a subframe that goes in. This plant did Mercedes and BMW cars. So at the start of the line, the parts would be stamped with a code, and that code was for traceability for the parts going through the line. And that's so that if there was a recall on a car or an issue, we could track it back both to that car, to that subframe, and then all the individual components that went into building that. And at the end of this line, we would take that same data that was stamped onto the part and print off a label. And so that label would be taken and physically placed on the part. And that would help us scan it throughout the plant and track things that are going through. So one day, it's a Tuesday, middle of the afternoon, nothing crazy. And then the power goes out. Only goes out for a couple minutes. It's a brownout that we get back home in Alabama fairly often. Everything comes back up eventually. Robots are running parts back through the line. But that label printer at the end of the line, no labels coming out. So I'm troubleshooting. It's pretty stressful for me because we're losing like $100,000 an hour. And this was my second job. It's pretty much just me here managing this. I barely knew what I was doing, right? And I eventually throw together a short-term solution. So we put a laptop plugged into the label printer, and people are manually typing in the codes to print off the labels. And then I'm frantically trying to troubleshoot to figure out what is wrong with this label system. Why is the traceability system not talking to the robots correctly? The reason this story really sticks out of my memory is because this was a 23-hour day for me. I think it was probably the longest like consecutive working nonstop day I've ever had in my career. Definitely the most stressful. And after tons of troubleshooting, really just at the end of my rope on what to try, I was like, okay, screw it. Let's just restart everything. You tried turning it off and on again. And guess what? That fixed it. Restarted all the robots, the traceability system, the label printers, everything came back up. And, further investigation, figured out this was just a issue. The state was out of sync, didn't come back up correctly. And the reason I'm telling you the story is that software design has real world consequences. A bad design could be the reason that you have to stay up all night debugging the label printer. And a little better design up front could help us all. have a little smoother career, smoother days. Design matters. So you want to start with good design in the small things and then work your way up to good design in the big things. So good design patterns at the application code level also apply at the architecture level. It might shift a bit, but in general, the same approaches apply. Now, what is design? Design is defining trade-offs. Design is preventing technical debt. Design is a system that grows with your organization. And really, at the end of the day, design is managing complexities. Complexity has to go somewhere. You don't really remove complexity, you just move it around. And so the real question of design is, where do you put that complexity? And it's all trade-offs. We'll start by walking through the solid principles. And so the solid principles were introduced by Bob Martin, also called Uncle Bob.
Oh, Ben, I think we lost the audio there.
Things are frozen.
All right. Give us 1 second here while we troubleshoot some internet issues.
And Ben appears to be back.
I think I'm back. I think you have to make me an organizer or panelist again, though.
It looks like you're showing as a panelist. So you should be able to reshare your screen.
Okay, let me make you co-host again, maybe.
Maybe tell me I can't share because
Okay.
it's disabled. Sorry about that. So
No
the
problem.
last screen you saw was the design screen?
Yeah.
All right. And
You're co-host again. You should be able to resume.
yeah. Okay. Should see my screen.
Yep. Your whole screen, not the presentation.
Yeah.
Okay.
All right. I'm going to jump back a couple slides. All
It
right.
was-
So we'll start here.
Yep. Sounds good.
Okay. Cool. So we're going to start with the solid principles. And this was introduced by Bob Martin, also called Uncle Bob Martin. The S in solid stands for the single responsibility principle. And it states that each software module should have one and only one reason to change. Like most things in computer science, this actually started with Dijkstra. And he came out with the idea of the separation of concerns. It was from his 1974 paper on the role of scientific thought. And he states, what focusing one's attention upon some aspect. It does not mean ignoring the other aspects. It's just doing justice to the fact that from this aspect's point of view, the other is irrelevant. It's being one and multi-track minded simultaneously. Here's an example for you. So here we have a user interface. Our user interface can both get an email and save a post. And what this does is this is going to mix our concerns. So the user object here is affecting both the users and the post. A better way to structure this would be to have a user interface that can get an email, and then have a post interface. And that post might have a user ID related to it, but it's going to manage its own saving, its own data manipulation. A little more complicated example, something like what you would see in the real world here, is an order. So we have an order. The order can get a total, get products, and get a PDF. The problem here is that now we're mixing the presentation layer with the data layer. So a better move here would be to separate the order and the PDF. So we're gonna have an order interface that can get a total and get product. Then we'll have the order PDF report that can set an order and can get a PDF based on that order. And so now we're composing that PDF report based on the order object. And this separates that role, right? So we're separating the presentation layer and the data layer. And the pain we're trying to solve here with SRP is, well, not even just SRP, but with this example, we don't want presentation layer changes to break the data object, and we don't want data object layer changes to break the presentation layer. We want to keep those responsibilities isolated. Here's an example. Just because you can doesn't mean you should. Next up is the open-closed principle. So the open-closed principle states software entities should be open for extension, but closed for modification. This was developed by Bertrand Meyer. So the full example of this is a little longer. So for open, a module is said to be open if it's still available for extension. For example, it should be possible to add fields to the data structures it contains or new elements to the set of functions it performs. Closed, a module is said to be closed if it's available for use by other modules. This assumes that the module has been given a well-defined, stable description, the interface, and the sensitive information hiding. So Bertrand is credited for having originated this term, open-closed principle, from his 1988 book, Object-Oriented Software Construction. And then what you'll hear a lot also is polymorphic open-closed principle, and that takes us a step further and says to use interfaces instead of just extending base classes. And most of the time nowadays, when someone refers to the open-closed principle, they're actually referring to polymorphic open-closed principle. Here's an example. So we have two jobs here. You can think of these as just two background processes that are going to run as a job runner, right? So we have these two jobs that are processed by a process worker. One is generating the job PDF, and the other one's looking up geolocation data on orders. And then somewhere we'll also have a process worker that takes in those jobs, and then based on the type of the job, it does different things with them in order to actually work through and process those jobs. The problem here is that we can't change those process workers without knowing how the underlying jobs work. We also can't change those underlying jobs without updating the process worker to know how they work. So this is now coupled together. If we want to separate this out, we would have a job interface. And that job interface has a process method in this example. And then we change the order PDF generator and the order geolocator to both implement that interface. And now they have a common method. We can simplify that process worker much easier now. That process worker knows as a job interface. It takes in any kind of job, and then it runs a process on it. It doesn't need to know about the individual jobs. The pain we're trying to solve here is that before, when we needed to make changes across both jobs and workers, and now changes in one or the other doesn't break the other place. We can now change the process worker without knowledge of what each job does. Open chest surgery is not needed when putting on a coat. And I have links to all these little memes. They're from Derek Bailey. I do not take credit for them. Next up is the Lescab substitution principle. This extends the open-closed principle by focusing on the behavior of the superclass and its subtypes. And so this was developed by Barbara Liskov, hence the name Liskov's substitution principle. I'm gonna let you read the full statement because it's not exactly easy to read out loud. But really, it's from her 1987 paper, or keynote rather, named Data Abstraction. And it's a complicated way of saying that we should be able to change instances of the base class to instances of a derived class, and it should still work. All right, so what does this look like? Here we use the kind of classic duck interface. So here we have a duck interface. A duck can walk and a duck can quack. And then we have our class mallard that implements the duck interface. It makes sense, right? A mallard can walk and quack. But now we have a rubber duck. So our rubber duck class implements a duck. You know, seems right. It is a rubber duck. But, you know, oh shit, rubber duck can't walk, can't quack. What would be a better interface for this rubber duck is probably a water toy. So, you know, a water toy is fun. A water toy floats. The pain we're trying to solve here is that using wrong abstraction makes things less clear, when an abstraction and interface should always make things more clear. A red flag when you're using interface or extending a class is that you have to define empty methods because you don't really need them, right? So if you find yourself doing that, if you find yourself defining, you know, an empty walk and quack method, you might have a duck abstraction. We really need a water toy abstraction. So it looks like a duck, quacks like a duck, but needs batteries. You probably had the wrong abstraction. Next up is the interface segregation principle. So no client should be forced to depend on methods it does not use. This was first formulated by Uncle Bob Martin while he was consulting for Xerox. He states that classes that have fat interfaces or classes whose interfaces are not cohesive. And the interface segregation principle really focuses on interface creep, right? So if you ever worked in a code base that had the all-encompassing user interface that does everything a user model or user object could ever do, you are probably pretty well with this interface creep. Taking this to our example before, right? So we had this order PF generator and the order geolocator that use that job interface. If we then needed a get lat long method in an interface, the job interface would be the wrong place to put that, because the order PF generator doesn't care about getting lats and longs. A better way to handle that would be a separate interface just for geos, and the geolocator can implement both of those interfaces. The pain here is using an interface and inheriting all of these things that you just don't care about. If you find yourself with huge interfaces that include the kitchen sink, you're probably doing too much with a single abstraction. Do one thing well, right? This box looks pretty dangerous, not very clear where you should plug that in. Last up for solid, the dependency inversion principle. High-level modules should not depend on low-level modules. Both of those should depend on abstractions, interfaces. Abstractions should not depend on details. Details, or concrete implementations, should depend on abstractions. This is also from Bob Martin. A handy catchphrase is code to the interface. You want to code to the interface, not to the implementation. And this also enforces that where appropriate, you want to use composition over inheritance. So here's a pretty simple example. So we have this post class that takes in a super user. Now this class is going to be very flexible because it always has to take in a super user. And it's going to have to know details about what that super user can and should do. A better way to do this would be to have a user interface. And the super user can implement the user interface, but now the post only has to care that it's taking in a user. This shows a little more flexibility. When now we have maybe a super user and a regular user, our post still works just fine because it only cares about taking in a user. It doesn't care if it's a super user or a regular user. The pain here we're trying to solve is we shouldn't need to know about the details when coding our implementations. We should allow the flexibility of only caring about the interfaces. That's kind of the point of the abstractions. here's a visual representation. Would you solder a lamp directly to the electrical wiring in a wall? All right, so next up, let's move to architecture patterns. This is the next level up. I'm gonna start this with a story. So this was also that second job, actually, so it's fairly early in my career. It was my first web application that I ever built. And this was back in the PHP 4.2 days. And a little tidbit, if you go look at the change logs from the website now, back then in the 4.2 days, this was 2005, they were announcing the release of the PHP Quebec conference on a CD-ROM. So I don't even own a computer anymore that has a CD-ROM drive. Anyway, so it's 2005. I'm working on my first web application with PHP. I'm using a hand-built framework. I really had no idea what I was doing. No version control. I'm using FTP to deploy things to servers. It's HTML and PHP and SQL just all together in SQL files, right? I had no idea what MVC was. And, you know, this actually worked pretty well. Everything's moving pretty fast. I could code like the wind, right? Because I knew where every single line, every single variable, I knew where it was because I wrote it myself. It was all pretty compact and very, very closely coupled. But then we added another developer. And that's when things really went poorly. We had 5 times the bugs. He couldn't understand anything that was happening. And it all fell on my shoulders to kind of support bringing him up to speed. And that is another hard lesson I learned of how even basic architecture knowledge goes a really long way, especially in teams. So we'll talk about application architectures. This is sometimes called components or component design. And a lot of the design principles we just discussed also apply at this next level up. So we'll start with layered or in-tiered design. And this is how you layer the concerns from your application, right? So, model view controller in VC was developed to solve this problem. And VC is a layered architecture. How do you separate your concerns? The S, O, and L of solid, ADR, MV, VCR, NVR, all these kind of popular web framework architectures or patterns. These are all developed to solve this problem. So what this looks like is this most basic level. You're separating your presentation, your logic, and your data layers. You could also be separating maybe your business logic and your domain logic. You could have different layers of data layers there, right? This could get exponentially more complex. This is kind of the main groupings you'll see. As your app grows, right? So maybe you start here, but now your app's growing, it's getting more complex. Your teams are getting bigger. You have more teams. The next step is to split this into domain-specific modules. And so not only do you have a presentation logic and data separation, you also have that same separation, but across different modules. These modules could be based around the function or the domain. These modules could be based on the team. You know, it's really up to you. Or there could be even more granular separations past that. This isn't all encompassing either. I mean, you might have libraries that are shared across these layers up and down. You might have libraries that are only live in a certain little part of this. Your most basic architecture that you probably started with, this is the one I started with that PHP 4.2 app, was just a client hitting a single server and had all these pieces in here together. It's like this one big ball of mud. But then eventually you start separating things out. The client's only hitting that one presentation part of that one module. But then behind that module, there's all this more complexity going around. And the complexity still exists, right? Like we didn't actually get less complex. We might have gotten more complex from this state to this state, but we've moved that complexity around to domains underneath. And it's easier now to build a mental model of where that complexity lives and how that works in each domain. The next architecture is microkernel architecture. This is also called plugin or prototype architecture. And this doesn't compete with in-tiered. This is complementary. And usually you'll see these used together, right? Like it's not like you have to choose layered or microkernel. You're going to use it all in the same app. Microkernel is loosely defined interfaces and components that play well together. So good examples of this are browser extensions or IDE plugins, or even just classes that implement interfaces, right? So you have a standard contract of how things should behave, and then you have other things that implement that contract. And then whatever you're communicating with, like your core, your app, doesn't even know the details. It just knows about that interface or that contract. This also can extrapolate out, so not just at the code level, but at the API level. So you have different services that know what contracts, what API contracts need to be implemented. They don't necessarily care what exact service they're communicating with or what server that service is on. They just care that that contract's fulfilled. If you have a well-defined interface, you can write tests more easily against this. You know how to test each service pretty easily. You can share a large part of your test suite. And as long as you know the contract is defined, it makes those tests pretty easy, and it makes the changes around that very state. A good example of this in the PHP world that you're probably familiar with is PDO. Right, so PDO allows you to swap the database engine underneath fairly seamlessly using the same API. So for the most part, your PHP code doesn't have to care what engine's underneath as long as you're using PDO. Now, there are a lot of caveats there, but that's the general goal. All right, next up is platform architectures. So we're talking about monoliths, service-oriented architectures, and microservices. And I want to really stress, right, like the reason I laid this out this way in a Venn diagram is that this isn't like a left to right progress bar. There's no right answer here. It's all trade-off. And any system of consequence is probably going to have all of these at once, right? There's no right answers. It's all about what's right at the right time. And no matter which architecture you choose or what state in this you are, the grass is always greener on the other side. There's just no right answer here, and it's all trade-offs. So let's start with monoliths. I'll talk through both pros and cons, and I'm not going to lay this out as like a simple pros and cons list, because that's really not it. It is truly just trade-offs. So what is a monolith? A monolith is a mono repo, so all your code lives inside one repo. It's deployed together as a single unit. So if you're deploying, 3 instances of your app, you're going to take that whole app bundled as one code base and deploy it as one thing in 3 places, right? This is all deployed together. It's often in a single language. It doesn't have to be. There's nothing enforcing that. Just usually is. And then, maybe you have a couple languages. Maybe you have PHP and JavaScript. Maybe you have a backend and a front-end language, and that can grow over time. And this is scaled together. So if you need to scale up to handle more load on one part of this monolith, you have to scale the whole monolith. Single endpoints can't be scaled separately. You're going to move fast here. In general, the greatest trade-off for the monolith is that your development speed is faster. It's on monolith. All the code is right there together. You can move a lot faster. You can collaborate easier. You can share code between teams much faster. But you will probably break things. Like in general, in a monolith, your code is more closely coupled together. And if team A makes a change, they're probably going to break team B at some point. Martin Fowler says that almost all of the successful microservice stories have started with a monolith that got too big and then was broken up. He doesn't recommend starting with microservices at all. He recommends starting with a monolith. Then when you actually need to scale, when you're popular, when your app's big, then you can worry about moving. So coupling with a monolith. Monoliths don't equal coupling all of the time, but I would say 99% of the cases I've seen, they're tightly coupled. That is both an advantage of the monolith and a disadvantage. So you have that faster dev cycle, you have easier code sharing, all the code is just right there. So I'm going to deploy something, I know that my service has access to all the shared libraries. That can also be very fragile. So if one thing breaks, you're going to have cascading failures throughout that monolith, right? So if I'm relying on the logging service, but team B goes in and breaks the logging service because they needed to change, now they've also broken my code and I had no control over that, right? Or maybe team B goes and makes a change to that logging service that they need, and they just weren't aware of the context and how I was using that logging service. And I say logging service, I actually mean like a logging library, like code inside the same monolith. And now they've changed the behavior of that. But because of the way I was using it, now maybe my code doesn't work the way I expected it to. Now, the best way you can handle this is with very good test suites, right? So if team A has great test suites from everything their team uses, regardless of the rest of the teams of the shared code, then they can more quickly surface that. But if you rely on just kind of shared tests of these libraries and just unit tests, then you're in for some surprises. Development speed is going to be a lot faster with a monolith in general. It's all shared, it's all right there. You're going to be much faster to market. You don't have to spend a lot of time thinking through your architecture. Usually, you don't have to spend a lot of time thinking through your tooling. You don't have to spend a lot of time on collaboration. Just collaboration between teams eat a lot of time. If all the code's shared together in one place, it makes all that a lot simpler. The maintenance, this is a double-edged sword, right? So maintenance for a monolith is both simpler to understand and easier to maintain early on, because again, it's just right there. A lot of times you can build an entire mental model of how the entire monolith works. But then as the monolith grows, that becomes harder, right? It breaks your mental model because it's too much to keep in your head at one time. You know, maybe at some point you have tens of thousands of files inside this monolith. And then at that point, just the complexity and the dependency graph of what's happening in there is unmanageable. And then there's a monorepo myth. You know, I've been referring to this as a monorepo. Really what happens over time though is a lot of times it's no longer a monorepo. It's a bunch of smaller apps tied into this one central location, right? So monolith does not equal monorepo, right? So you have now broken up your monolith into a bunch of applications inside the one monorepo. It's a small word difference, right? Monolith versus monorepo, but it matters. So a lot of times when we're talking about a monolith, what we actually mean is a monorepo. Now, one of the main advantages of a monolith is that it's trunk-based, right? So it's trunk-based development. Everything's always at the latest head. You're always using the latest version. If you need this library over here, you don't have to worry about what version or what changes in there yet. You just use it because that's the latest one. If you need to make a change to endpoint A or to library A, you know that that change is going to be affected across all the code bases, across all the apps inside that monolith. This can also lead to a dependency hell though. You know, so maybe team B makes that change to that library and now they've broken team A's code. If that had been versioned, then it would not have been a breaking change. Team B could have rolled forward with a new version, used that, and then team A would have still been functional in that older version. But that's also a lot of overhead. So now you have to worry about what release am I on? I have to cut a release. I have to maintain a change log for each version. I have to keep track of what parts of my code are using which version, right? And so that dependency graph becomes pretty huge to manage. And now you've taken away a lot of the advantages of this model. The scaling for a monolith. Like I said, everything's scaled together. And so this can be really great for simple horizontal scaling, but it can be really bad when we have one part of the app that needs to scale more than the rest of the app. So let's say we have like a shopping cart, we have an admin page. Both of those need to log the same, right? And so the shopping cart is getting 50% of their traffic. The admin page is getting 50% of their traffic. But now the logger is getting 200% of the traffic, right? Because it's getting traffic from both of these thrown at it. And if we could scale this separately, we would spin up 2 logging instances or 4 logging instances. And then we could just throw those logs at that logging service. We can't do that on a monolith. That's one of the big downsides here. So it makes that scaling much simpler. We just add more servers. We just deploy more instances. But it does make it harder to more fine-tune that scaling. So next up, what you usually see is you'll see a monolith gets popular, a monolith needs to scale, and then you start moving to SLA. A lot of apps never get past this point where it's monolith and SLA, and that's fine, right? There's nothing wrong with that. SLA is service-oriented architecture. A lot of people think service-oriented architecture and microservices are interchangeable, but in my opinion, they're not. They're two very different things. So all microservices are service-oriented, but not all service-oriented architectures use microservices. And the way to think about service-oriented architecture is the single responsibility principle that applies to services. SOA is more loosely coupled. It's not always fully decoupled, but it's at least more loose, right? Isn't like a specific place in the scale of how tightly coupled or decoupled services are. It's up to you to define, and that'll change over time. It's never going to be a static thing. You're never going to say like, oh, everything's fully decoupled and it stays that way. It's going to be a state you have to work towards. The first boundaries you'll usually see on SLA is around team ownership. Usually you hit this point where it's really hard to manage changes to this one code base across multiple teams. And so you'll end up cutting up the monolith into multiple services based on that team ownership. For example, like the reporting team needs to ship at a different frequency than the shopping cart team. And so if you're in that monolith, you have to ship it all together, and that can be a real pain. But if you chop that up, you can ship separately. Also, another example is select a logging service I gave before. So you have a logging service that needs to scale separately. You'll chop off that logging service, and now you have your own thing that you can ship, deploy, scale at a different pace. Once you get into SLA, this is probably your first foray into APIs as first-class citizens. It's when you start thinking about communication by RPC instead of just local procedural calls, because you don't have all the code right there in one place. You can no longer call that code directly. Now you need to go over the wire or use some kind of call mechanism to communicate. This is also when authentication and authorization become pretty huge concerns. You know, how do you safely communicate between these services? And one of the main advantages here again is the ability to scale separately. So if that logging service needs to do 10, 20, 30x what the little small pricing service needs, that's not doable. You can scale this separately. Some more questions come into play here though, some more complexities, peering out. How do we route? How are we routing between services? What you'll see often in an SLA is that you'll be proxying requests through some centralized gateway. And so there'll be a centralized API or centralized gateway that everything routes through, and then that gateway will know where to send things. Also, how do you discover services now? Usually in SLA, you're going to have that gateway, and that gateway will know where everything is. But as it gets split up more, that can be harder to manage. And so you have to start thinking into how can peers discover their own services. Then you can also have many monoliths. You especially see this in SLA because you might take this one huge app and cut it in 2 or 3. And this isn't really a microservice. These are still 3 huge services, and they're really still monoliths, but now you have 3 of them. This can be good and can be bad. This is also often where you move to multiple repos. So you'll often go from this one big app in this one repo to maybe 3 SLA services, and you'll move this into multiple repos. But you don't have to. It's fully possible to maintain a mono repo as you split things apart. It might require more tooling on your part to manage that, especially around the deployments and how do you chop off pieces of code for deployment. It's very doable. Google and Facebook are well known for still using mono repos, even at their scale. Wayfair, for the longest time, has used a mono repo. We've only recently started moving towards separate repos. And mono versus multi-repo is really a question of dependency inversion management, more than it's a question of the architecture. So be careful not to associate those as a one-to-one. All right, and then lastly, let's discuss microservices. So microservices should be loosely coupled, but it's still really easy to build a coupled microservice. Only now you've coupled to a system that's completely outside your control, right? So like before, when you were in this monolith, you were able to just see that code and use it, and that was too coupled. Now there's a service that exposes an API, and you're completely coupled to that, but you have no real visibility into the changes that are happening there. And that's something you have to manage. And there are tools and ways to do that, but it's a complexity you have to think through. Deployments. So now you can individually deploy smaller services to these microservices. This will often remove the need for like a batch deploy. So often you don't deploy multiple things at once. You can have small pieces that are deployed independently, these smaller units of code and deploy. But this can also get more complex, right? So now you have to start thinking through, am I going to use trunk-based deploys, or am I going to version each deploy? Is each microservice going to have its own version? You know, how do I coordinate a deploy? If I need to make a change across, you know, the payments and the cart, and they both need to have a similar change, or the similar feature needs to be deployed together. How do I coordinate those deploys for the separate services? Also, failed deployment. So you have a coordinated deploy to the pricing service in the cart. What happens if just one of those fails? How do you roll that back? What happens if a change to that pricing service fails on its own? What do you do? Do you use trunk? You could use trunk. You say every service uses the latest version, but then you're getting pretty close back to that old state where it's very easy for another team to break your code. Scaling, that's probably the best, you know, advantage of the microservice. You're able to ultimately, you can scale completely independently of everything else to whatever your microservice needs. But more services equal more problems. So you've just moved complexity from the application level to the infrastructure level. And there's a lot more questions you need to answer now at the infrastructure level that you no longer have to worry about at the application level. So how do you do service discovery? How do you do a circuit breaker? How do you do blue-green deployments? All of that. Tooling is really key here, right? You need tooling to manage your infrastructure and then the communication between those services. You have to be really careful as well not to build a distributed monolith. There's no point in taking exactly the same thing you had in this one code base that worked well and just distributing it to 1,000 services. That's going to blow up your complexity. Any system of scale, any large scale system is going to be using all of the above. It's going to be using monoliths, SLAs, and microservices. There's no right answer here. It's all just trade-offs all the way down. You need to pick the best tool to solve the problems at hand. And make sure not to chase fads too, right? Like I myself, several years ago, was all in on microservices. It seemed like the answer. And then once you get pretty deep in there, you're like, oh, wait, these same problems are happening again. They're just at a different scale. You know, now they're at the infra level instead of the code level. Microservices can be amazing. I actually love them for the right problem, especially in complex systems with a lot of teams. It can be really great, but also monoliths can be incredibly refreshing for developer velocity and how quick you can move. So it's all about balancing those trade-offs and figuring out what's right for you and your team, your app, your company. All right, the next layer down from this is data architectures. And I got one more story here for you. So I was developing an electronic application system for insurance companies. And so this is a system where you would go in and get a quote for an insurance application. It would store your application, it would run validation on it. You would get rates, and then the end of the process, you would receive an insurance application, right? So you're like, do you get life insurance? When we started this process, there's one specific part in here where we have this SQL schema laid out, and one of the fields is var car 200, and that was plenty for what this field stored, and it was a middle initial or something like that, right? And it seemed fine. We had validation around it. It worked great. But over time, the specs of the system changed and the systems diverged. And so we had this kind of one static system, and then we had an API get written on top, and then we had the front end be decoupled. And so now we have these multiple systems feeding into this API, and they might have their own validation, but the API never got the validation to enforce that character limit. The character limit was only enforced at the database level and on the front end. So at some point, we had an app get written that didn't enforce that at all. So now invalid data that users try to save would go past that limit, the database insert would fail, and then we didn't save that app at all. So that app just was not saved. This was pretty easy to see through our logging, tracked it down pretty quickly. It wasn't a huge deal, but really the point I want to make with this is that your data architectures usually outlive the rest of your choices. And your data is pretty easy to ignore. Pretty often, as long as your data is working okay, you don't really think about the data layer. You think a lot about the code and the application and the infrastructure, but your data is probably going to outlive most all of that. So while the rest of your stack is changing pretty quickly over time, those data decisions really do matter. So let's talk about what these data architectures will look like. We have SQL databases, which is usually a relational database. We have NoSQL databases, which there are several options to choose from. So a relational database will be something like MySQL, Postgres, MS SQL. These are probably familiar to most web developers, probably to most people here. And they're definitely the most popular for web apps. NoSQL databases are things like MongoDB, CouchDB, Redis. This includes document DBs, key value stores, graph databases. There's also time series databases, which are sort of NoSQL databases, but also their own thing. Now, these are becoming really popular for things like event sourcing. And this includes like InfluxDB or Timescale DB that's built on top of Postgres. And then in the real world, what you usually have is a combination of different kinds of databases. So you might have, one database that does multiple functions. Maybe you have a Postgres database that's relational, but then suddenly you need to store some non-relational data and you throw that into a JSON B field in Postgres. Or maybe you actually have just different databases in production in your architecture. So you might have like a Redis cache in front of MySQL. Now you're using a combination. Scaling of data often involves breaking rules, especially breaking third normal form. That's saying you have to know the rules before you can break them. Sharding will involve splitting up data across multiple servers and changing the way the data is stored. And a lot of times you'll be adding caches to data, and that'll involve those combinations, right? So if you have relational data, you'll probably be adding a key value store for caching on top. At some point when you scale, you're going to have to start worrying about separating your reads and your writes, or sharding by region, things like that. And then more and more as you scale, you'll be doing unintuitive things based on how the data is used, not necessarily how the data should best be laid out. And always remember, having a coffee in the morning doesn't wake you up. Try deleting a table on a production database. Even to this day, working with production data is probably the most stressful things I do. All right, so I want to finish this talk with an example design and walk you through kind of some thought processes in the life cycle with scaling a service. We'll start with another story. So that same insurance application I told you about before is calculating policies for insurance apps. A part of that was the actual calculation. So you put in like your age and your date of birth and your zip code. It'll run a ton of calculations and give you a rate for a policy. We had a system that did this, and it had like 12 different products that you could choose from. So we would take your information first and then calculate these 12 products. Each was a module in the front end system. It would call an API asynchronously. It would get the result back. It would give you a preview of what the rates were. It was a really well-designed system, right? Like it was full SRP, everything was abstracted, everything used a service. It was great until we rolled it out to the client's horrible network. And the client's network just could not handle all of this network traffic for every single user. It was just completely unbearable. Now, here's where we ended up breaking a lot of the rules. So what we did was we took this PHP service, well, each one of these PHP services, we refactored them into JavaScript modules. Then we wrote a node service that could serve the calculations still as a service, but also that JavaScript module could be used inside a browser. So you could either use it in browser, use it in Node, and it's the same code underneath. But now we were able to stay pretty close to the same architecture, but we could call those services inside the browser without needing to hit the network at all and fix that issue. The point of that isn't that that was necessarily a great design, but the point is that no matter how perfect your system is technical, if your user's experience of it is poor, you have a problem to solve there. And it's trade-offs all the way down. There's no perfect system. My colleague at Wayfair, John Biddle, always says, you win through iteration, not through getting it right. So what he means is it's more important to be open to changes than to get it perfect. Don't prematurely optimize. All right, let's go through this example. We're going to do an example of Pastebin. If you don't know, it's pretty similar to like a GitHub gist. It's a system where you store code and retrieve code so you can share it around. So here are our basic requirements. We need to be able to save code with a unique URL. And then we need to be able to retrieve that code via that URL and don't break it. We're going to paste in code as plain text and then save that. Let's talk about how we're going to scale it. When you think about designing a system and scaling it, you're always going to work with initial assumptions. You need to just acknowledge that these are assumptions and they won't be right, and that it's more important for you to keep your system open to changes later than it is to get it perfect. And then you need to try to find the balance between, premature optimizing for when your Facebook level scale, which most apps never get to, and not going too far the line where if you get a single post on Hacker News, you go down immediately, right? You need to find the right balance for you and your app. So let's start with something pretty basic here on the scale. Let's assume a 50-to-1 ratio of reads to writes, right? Because with a Pastebin, we're probably going to need a lot more writes or a lot more reads than we do writes. So let's say we have 50 reads per second and 1 new paste created per second. And we have a 10 kilobyte average size of a paste, right? So here's that math laid out. And that's going to equal, we need 864 megabytes of storage per day. And that 86,400 there is just the number of seconds in a day. All right, so when I'm scaling a system like this, especially for like a startup or something new, I want to make sure the data model, I like to be able to scale for multiple years, but the data storage itself and probably the system scale itself, I like to be able to scale for about 6 months. Right, so if you're always thinking 6 months in the future, you can keep iterating on that. You just need to keep yourself open, not to solving the problem for the next decade, but to solving the problem for the next 6 months, which helps give you a nice constraint to design around. So here we have 864 megabytes a day, 30 days in a month, 6 months. That gives us 155 gigabytes that we need to store. And then let's add a buffer to that because we don't want to get tight. So we're going to add a 25% buffer. That gives us 193 gigabytes, and let's just round it up to 200 gigabytes for 6 months of storage. 200 gigabytes really isn't much in modern day databases. We can handle that with 1 database server pretty easily. What does our API look like? Let's keep it simple. Here we're just going to have a GET request with the primary key for the URL and then post. And that'll be how we retrieve and store these pastes. And the first version of our data model is going to look like this. So we're going to have an ID, which is a serial. Just think of it as an int, +1 each time. We have our content, which is a text field, and that's going to be the actual pasted code. And then we have created that timestamp. The most basic system that would probably solve this is just a client hitting an API server that hits a single database server. This is going to solve this problem most of the time. Now, when you're designing a system, it is important to kind of throw out scenarios, talk to your business leaders, your product people, whoever you're working with to design this, and think through some scenarios of how they could see this being used or how this might need to scale in the short term. So the scenario we're going to design for here, the next iteration of this, is the IDs are becoming too long, right? So users are typing in these IDs or they're typing in these URLs, and suddenly the URLs are 10-digit integers at the end of that, and that's really hard to keep track of when you're typing it in. So product's worried about that. The other concern product has is they don't want people guessing the next person's URL. You don't want people to just increment by 1 and guess the next URL. How we solve this? So let's solve this with hashing. And let's figure out what kind of hash algorithm we need here. All right. So I said before, I'd think about 5, 10 years out. I'd think multiple years when I'm thinking about the data model itself. So here we're going to go big. We're going to say 10 years. So here we know we have 86,400 inserts per day. And if we take that out by 10 years, we need 316 million hashes for this data. So 316 million unique pieces of data over 10 years on average. what would it take to do this? So we can actually do this pretty easily. You know, base 64 encoding, 4 digits, that'll give us 16 million. If we want some buffer, we could go to 5 digits. That'll give us like 300 million. So we update our database. You know, instead of using an ID that was serial, we now use a hash. This is WARCAR 4. The rest is the same with content and created out. Then our API now looks like this. So when we're posting, we're going to need to generate the hash. We're going to need to check the hash to make sure that it hasn't been used again. And then we're going to need to save the data. So that hash could be a lot of things. You know, that hash could be, you know, we just generate maybe an MD5 or a SHA-1 against the content, and then we grab the first 4 characters or random characters from that. It doesn't quite matter how we seed that, as long as it's random enough. And then we check to make sure that it's unique before we save it. If it's not unique, we're going to need to regenerate that. This is what that would look like. Anyway, so this will look pretty much like it did before. The one difference here, so this is our next scenario. We're going to add this key service. So this is actually getting an SLA now. So now we know we just have the one API. We now have a key service that's generating key source on the fly. The kind of great optimization we can make next here would be storing these keys, right? So maybe we don't actually need to make them on the fly. Maybe we store them in a data set, then we can just pop them off the stack. So this makes our whole process of saving data faster. We no longer have to generate this hash. We just have these hashes stored in a data set and we pull them off. There's a few optimizations we can make here, right? So like either we keep them in a database, that might be slow. Maybe we keep the next 1,000 hashes in Redis or in some type of in-memory queue, and we just pop those off the stack to use as we go. These hashes just need to be unique. They don't actually have to represent the content. Now our API is actually a lot simpler now too, because we just need to get the hash. We know it's going to be unique, and then we can save it. The next problem we might have, the next scenario we could think of, would be that large paste are filling up the database. You know, that text field for content is getting too large. So what if we take that content field completely out of our relational database? So now we just have the hash and the query to that. You know, in the real world, we probably had a lot more metadata. And we move that actual content to object storage. You know, maybe it's an S3. And that storage could just be keyed off that same hash, that 4-digit varchar. This also allows us a little flexibility, because if we're using a full object store, we're not limited to just plain text anymore, right? We can store whatever we want in there. Another great thing this does is this allows scaling of the database and the object store separately. So here what we have is we have the client hitting the API. It uses the key service to bring back a key, and then we're storing our data in both the database and object storage. This will almost definitely scale to our previous needs. This is what the API looks like now. So we're going to post, we get back a hash, we save it to the database, and if that saves successful, we save the object. What if we need to scale more? What's the next version of this look like? You know, probably the next version of this looks like adding a cache layer between our API and the data, you know, a data caching layer. Maybe we want to cache the most 20 recently used pieces of data for the reads. Maybe we want to cache more than that. We can have multiple cache servers. Next steps could be more caching. Next steps could be load balancing. Could be separating our reads and our writes to different systems. Could be a reporting system. So maybe we need a reporting system to report on our paste activity and our stats. And we don't want that reporting system to put at risk our day-to-day work. So maybe we want to have a separate database that mirrors our prior database that we only run reports off of. Here's an example of what this next step could look like. So now we have multiple services. Maybe we're moving towards microservices. Another version could be we have cached requests. Another version is now we're sharding databases. Now we have microservices. Now we have multiple cache servers. You know, maybe we need multiple availability zones. Whatever. The most important thing is that as that system changes, you can change it with it. You don't need the correct design. You just need the next iteration of the design. You don't need to think about the next 50 iterations, just the next iteration. As long as you're growing, you'll continue having scaling problems and you'll continue to figure them out. It's a good problem to have. Iteration is key. All right, that's the last thing I want to leave you with. I'm going to drop some resources here in case you want to learn more. Uncle Bob Martin has some very good books on design and architecture, Clean Code, Clean Architecture, and Clean Coder. Martin Fowler, this book is good. I would also strongly recommend his blog. I would probably recommend his blog more than this book, but definitely check out both. Also, if you want to delve into microservices, Microservice Patterns is a great book. It does have all its examples in Java, so that's maybe a downside for PHP people, but it's always great to learn from other languages where we can as well. That's all I have. Thank you for your time. I will mention too that at Wayfair, sister team of mine is hiring for a .NET Java staff engineer on our development platforms team. So if you think that'd be a good fit, please reach out. I'm really interested in finding my next coworker. And thanks for having me.
Awesome. Well, thank you so much, Ben. Looks like we ended up having a few people join us, attendees here on Zoom, and I think it went smooth, except for that middle part where you disconnected for a few minutes, but it's all good. I think Ian was monitoring the chat. I guess I had a couple questions for you. And then we could get into some of the Q&A questions here. So, say you have a, I guess I could switch back over to the preview image there, so that doesn't show our faces on the video, but yeah. So if you have a Vue or a React app, right, like a JavaScript front end, and you're communicating with the Laravel back end, and it's just an API. At what point is that a monolith, and when does it start becoming more of like SOA flavored? Is it if it's like in the same repo or separate repos? Like how? What's the breakdown for you look like on that?
Yeah, like in general, I would say don't try to box it in like that and don't care so much. Because I feel like once we start labeling it, then we start worrying about doing the right thing. And that's probably a failure path. If we had to box it in, I would say that's probably still a monolith, right? So you still have like one front end communicating to one back end, and you probably have a large API. That's not a bad thing. That's fine if that works for you. At least then you do have some flexibility in where you store that code. It doesn't have to be in a monorepo. You could keep your front end and your back end code separately. And that's fine. Really, if that works for you, that's fine. The place where I would start thinking about separating that is if you're hitting either team boundary issues to where people are getting in each other's way, trying to make changes or coordinate changes across software or new features or whatever, then that's probably the time to break it up. Or if you're hitting a point to where you're having the scaling issues, right? Like you're having to deploy this huge Laravel app to 40 servers just because this, your one geolocation server needs a lot more power. Maybe that's time to break off that geolocation service and then it can do its own thing and then you're communicating to that separate service, right? That's how I would think about that path.
Cool. So there's definitely some gray area in that like transition phase between monolith to microservices, and you're kind of the opinion is perfectly fine if you have multiple monoliths, as long as things are scaling well and it's working for you at your scale. Why change it?
Yeah, pretty much. And I'm a pretty strong believer that the pain will show you where you need to make changes, right? So if you find yourself repeatedly in pain, and by pain I mean like, you're waiting an hour to deploy your change, or maybe 4 hours, and that's some pain that you need to solve, and you need to figure out what's causing that and what paths you had to break that up.
So like team agility could be a factor in kind of moving to more distributed architecture.
Yeah, totally. And I've seen that go both ways, actually. So like I've been at companies where, we had 5 people and we had 50 microservices, and that definitely hurt the agility. And then you go backwards and then you start going to, maybe 5 monoliths, and that increased agility.
So it's like it's a balance. You could go too far in one direction. So I guess, in terms of team size and, containers is a big thing now. Kubernetes, is taking over the world, and kind of doing everything in, in containers. Do you have any, I'm interested to know, like, any opinions on, like, in terms of, ease of scalability, like when do containers help? There's certainly if you can scale things just as well without containers, depending on the host. But at what size kind of team and depending on the structure, does it make sense to move to like a completely containerized application setup?
Yeah, that's probably mostly a structure of maybe even the size of your company. I think containers in Docker make a lot of sense early on, even no matter if you're one person, right? It's very nice to be able to just, let's say you're a freelancer, you're a single person, it's super nice to be able to just go into whatever client project you're using that day, boot up the container, and it just works. That's just an incredibly nice workflow rather than trying to like change your local environment for each client to make that work. And the same thing you can apply to the company, right? So you're a 3-person dev shop, you have this one app, but now you need to onboard a new developer. Do you really want to waste 2 weeks trying to get his environment figured out when he could just boot up an image? So I would say containerization is worth doing super early. I don't think there's many cases where it's not worth doing. As far as like Kubernetes or where you're deploying to, that's a different kind of ballgame. And Kubernetes is very complicated. I don't recommend it for smaller teams. I would recommend pick a cloud service and go with what they do there. So go with AWS, go with GCP. Don't try to run your own servers unless you are incredibly comfortable doing that, and also you want to for some reason. Because I'm comfortable with it, and I still choose not to most of the time.
So keep it simple for smaller teams is kind of what you're hearing from you.
Yep.
And I think I agree with that as well. So that's good. Good to hear. You're confirming that. Great. So Ian, do you know if there was any questions on the YouTube's? I think you're monitoring
No
that.
questions on YouTube.
Okay. Awesome. Well, Ian, unless you have any questions for Ben, I think only the 3 of us can talk at will. We'll end it there for this month. I really appreciate you coming and talking. I think we're on the right direction with the meeting this month. There's some technical issues with the one last month, but yeah, really appreciate it, Ben. So it's good to see you again.
Thanks for having me.
Yep.
Take care.
All right. Thanks. Bye.